Welcome back, everyone. Today we are moving on from simplifying our trigonometric expressions into verifying trigonometric identities. So we need to talk. Think back to geometry. You remember the word proof? Well, that's what we're doing today, just not like we did in geometry. Okay, so we're actually doing actual proofs of trigonometric identities. Okay, so let's talk about how we're going to do that. We're going to use our fundamental identities from this chapter that we've been dealing with all week to actually verify new trigonometric identities. And when you verify an identity, you need to, here I'm highlighting this, begin begin with the expression on one side. So either on the left side or on the right side. And then we're going to use algebra and trigonometric properties to manipulate the expression until it is identical. So it has to be exactly the same as the other side. So pretty much, if you look at example 1, we can either start on the left side or on the right side, and we're going to manipulate. Let's say we started on our left side. We're going to manipulate the left side in order to get exactly the same what's on the right side. Okay, let me erase that. You want to notice that when you verify an identity, it's not the same as solving an equation. That's really important because when you verify an identity, you cannot assume that two sides of the equation are equal because you are trying to verify that they are equal. We don't know if they are equal, so don't add and don't subtract something from both sides of your equation, or multiply or divide or do anything, because that equation is not actually an equation. We need to verify that it is true. Okay, so you cannot use any of the properties of equality, such as adding the same quantity to each side of the equation, okay? Because it's not an actual equation. We're verifying that it is an equation. All right, so let's begin. You may start on the left side or on the right side, or you can technically meet in the middle. I'll show that in the last example. So the way I see it is I take a look at that identity, and I need to verify that it is an identity, that it's actually equal. So I usually start on the harder side. I pick the hardest side and I manipulate it and I simplify it until hopefully somehow or another I'm going to get the right hand side. So let's start. I'm going to go on the left hand side. And I'll arrive at the end with sine squared theta in the end. So on the left-hand side, we're going to start out with secant squared of theta minus 1 over secant squared of theta. Now, I think, what can I simplify? So you're going to use all your simplification techniques that we've done all week, and you'll notice that we've got a Pythagorean theorem identity right there. Secant squared theta minus 1 is equal to tangent squared of theta over secant squared of theta. Now we can rewrite that with sines and cosines. So let's try that. Tangent squared of theta is just sine squared of theta over cosine squared of theta. And that's being divided, I'll write it side by side first, divided by secant squared of theta, which technically, keep going, sine squared of theta over cosine squared of theta is just, we'll divide by 1 over secant squared is just cosine squared of theta. Now we can multiply by the reciprocal. Look, I'm not multiplying both sides of my equation, right? I'm not doing any properties of equality as I prove this. So sine squared of theta divided by cosine squared of theta, multiplied by your reciprocal, cosine squared of theta over 1. And now we can simplify. So cosine squared of theta. And look, what do we have at the end? We're left with sine squared of theta. So we connected. We have a little proof story. We proved that the left-hand side is actually equal to the right-hand side. And you need to make sure that if there was any sign or anything, you have to have exactly the right-hand side in order to verify it. All right? So we know that since secant squared theta minus 1 over secant squared theta is equal to all the middle, it's actually equal to sine squared of theta. All right, another example of this idea of verifying the identities. For this one, I think I'll start on the left-hand side again. It looks a little more complicated. So my left-hand side is 1 over secant theta minus tangent of theta. As you do these, you really have to show every single step along the way, or it's not necessarily true, right? Kind of like your proofs from geometry, you have to show every single step along the way. So for this next step, I'm just switching to 1 over cosine for secant and sine of theta over cosine of theta. I don't know if that's going to help me, but let's give it a shot. Just a shot in the dark. We can combine that denominator. So 1 over, let's make common denominator. We have 1 cosine of theta. So 1 minus sine of theta. So now you're like, well, I don't know. Let's try something. I'm going to just break up that fraction and go 1 divided by 1 minus sine of theta, maybe multiply by my reciprocal there, get rid of the fraction on a fraction. So this is 1 times cosine theta divided by 1 minus sine of theta, which, I mean, do we need the 1 times? No, not really, so let's get rid of that. So cosine of theta over 1 minus sine of theta. Now, this gets a little tricky, right? I don't really know what to do at this point because what do I need? I need a secant theta plus tangent of theta. So I'm showing you a real new technique, new trick. Keep it in your back pocket for any time that you need it. And we're actually going to take that denominator and multiply by the reciprocal. Or not the reciprocal, sorry, the conjugate. So 1 plus sine of theta, numerator and denominator. So I'm going to force one of those Pythagorean theorem identities to happen. Okay, that's my goal here. And we can distribute a little bit. So cosine of theta plus cosine theta sine of theta. That's in our numerator after I distribute. And then our denominator will be a nice little Pythagorean theorem identity. After you FOIL it, be 1 minus sine squared of theta. Okay, now let's replace that. So my eyeballs, that's my happy face, Pythagorean theorem identity. You've got, hurry. You've got, let's see, leave that numerator, so cosine theta plus cosine theta sine of theta divided by 1 minus sine squared of theta is just cosine squared theta. All right, so how does that help me? What do I have? I have actually a GCF in my numerator. So I'm going to take that out, cosine of theta, and what's left would be 1 plus sine of theta, which almost looks like a Pythagorean theorem identity, but it's not quite, right? So cosine squared of theta. Now we can cancel out a cosine in our numerator and our denominator, and that breaks it up into 1 plus sine of theta over cosine of theta. And you might have honestly lost track of what the heck we were even trying to prove. We need a secant of theta plus a tangent of theta. And don't we have that if we were to just break up this fraction? So 1 over cosine of theta plus sine of theta over cosine of theta. All right, and that gives us secant theta plus tangent of theta. And that is our full right-hand side. All right, so our nice little proof story. Whew, it's kind of a long one, sorry. You've got your left-hand side connects and is equal to our right-hand side. That was one way to verify that identity. Maybe some of you, I'm going to show you another way, are like, whoa, that was way too much work, right? Some of you, if you had seen, another way. So we started off, we wanted to verify 1 over secant of theta minus tangent theta, and verify that's equal to secant of theta plus tangent of theta, right? So I'll show you another little trick. If you had taken, we'll start on the left-hand side of 1 over secant of theta minus tangent of theta. We need to connect, okay? One way to get kind of pretty far really fast is to take that denominator, right, and just right away multiply by your conjugate. So your conjugate would be secant of theta plus tangent of theta, numerator and denominator. All right, so that would be left with secant of theta plus tangent of theta over secant squared of theta minus tangent squared of theta. And if you were super keen, you could notice that that guy, secant squared of theta minus tangent squared of theta, is just a Pythagorean theorem identity version. And you get secant theta plus tangent of theta. That denominator is just equal to 1. And there you have it. Super short. Sometimes you see the long way to verify these, and sometimes you might be able to see the shorter way. Either way, I would count it as correct. All right? Our next example, we add a little extra layer. So we've got verify the identity. I'm going to start again on the left-hand side. It looks a little more complicated with that secant and the tangent for me. So left-hand side, start there. Secant of x plus tangent of x. I'll switch it all to cosines and sines. So 1 over cosine of x plus sine of x over cosine of x. So at this point, I can combine my fraction. I already have common denominators, so that gives me 1 plus sine of x. So in the last two examples, we multiplied the denominator by the conjugate, right? So you can also multiply the numerator by the conjugate, or even sometimes itself. So multiply by conjugate, either numerator or denominator, whichever helps you the most. All right? So I'm forcing a Pythagorean theorem or a Pythagorean identity to happen when I do this. And the more you practice these, the better you'll get at spotting them. Okay, when I see a 1 plus sine of x, I know I kind of want a 1 minus sine squared of x to happen. So that's a tip off of when I want to multiply by the conjugates. All right, so multiply, FOIL out your numerator, you get 1 minus sine squared of x, which is what I wanted to happen, divided by cosine of x multiplied by 1 minus sine of x. And I'll leave that cosine out there because I know I'm going to end up canceling eventually a cosine when I use my Pythagorean theorem of identity. So 1 minus sine squared of x is just cosine squared of x. Now that gets divided by cosine of x multiplied by 1 minus sine of x. All right, we can cancel out a little bit. So cancel a cosine out of numerator and denominator. Now we're looking at cosine of x over 1 minus sine of x. And I mean, at this point, oh, look, hey, that's the right-hand side. Sometimes you just run with a few ideas that you have and you end up at the right-hand side, which is what you're trying to prove here. All right. So lessons learned, multiply by conjugates. You can also, not similar to multiply by the conjugates, just take the numerator and multiply by itself, numerator and denominator. So instead of like 1 minus sine of x, you could go 1 plus sine of x, and that'll give you like a little bit longer expression, but sometimes that's helpful too. Example 4, we're going to verify this identity. Obviously, I kind of want to start on that left-hand side. If I started on the right-hand side, if I started at 1, I don't really have any idea how to get the left-hand side out of 1. So hopefully that makes sense. So sine of x over cosecant of x plus cosine of x over secant of x. All right, so I see secant and cosecant. Let's get rid of that. Let's just go change them to sines and cosines. So sine divided by 1 over sine of x, which that looks weird. We can fix that in a second. Plus cosine of x over 1 over cosine of x. Now simplify that. We know that sine of x divided by 1 over sine of x, right? Most of you don't really need to show this step for me. I'm cool if you just jump, but since, you know, it's all online, I don't want you to get lost in a step. So this is really just sine squared of x after you multiply by the reciprocal, and cosine squared of x. And hey, isn't that our Pythagorean theorem identity? And that is equal to 1, which is our right-hand side. So our right-hand side is definitely equal to our left-hand side. And we used all of our identities to prove it. All right, example 5. We're going to go, and for this one, for the most part, most of the time, 99% of the time, you'll start on the left-hand side unless you get stuck. So let's go left-hand side again. So tangent squared theta minus sine squared theta. Kind of like my shot in the dark is really just switch to sine and cosine. So sine squared of theta divided by cosine squared of theta. and minus sine squared of theta. Now I'm like, well, I could combine those fractions, so let's multiply by a common denominator of cosine squared theta, so I can combine into one fraction, and that would leave me with sine squared of theta minus sine squared theta cosine squared theta divided by cosine squared of theta. All right, so now I'm just left with one fraction, and you'll see you have definitely a GCF we can take out. Let me change back to blue so you guys can see it well. So let's take that out, sine squared of theta, and our leftover would be 1 minus cosine squared of theta all over cosine squared of theta. And that is really nice because here's one of our Pythagorean identities. So let's replace that with our sine squared. So we've got sine squared theta times sine squared theta over cosine squared theta. All right, now what am I trying to do here? I could combine that into sine to the fourth, but is that really helping me prove the right-hand side? Not really. Agreed? So what do we need? We need a tangent squared of theta, and I already have a sine squared of theta right here. So break this up. Sine squared of theta over cosine squared theta multiplied by sine squared of theta. That really gives me my right-hand side of tangent squared theta times sine squared of theta. And boom, that is your right-hand side, and that proof is done. So left-hand side is equal to our right-hand side. Now, I'm going to show you how to meet in the middle. So when you need to transform both sides of an equation, sometimes it's easier to transform both sides of the equation separately into a common form. So the following suggestions may be helpful as you verify trig identities. You may substitute one or more basic trig identities to simplify the expression. You can factor or multiply or simplify an expression. You can multiply the numerator and denominator by the same trig expression. You can also write both sides of the identity in terms of sine and cosine only, then simplify each side as much as possible. So a few more helpful hints. We've kind of already talked about those. Example 6, we're going to meet, or what I call meet in the middle, to verify the identity. So sometimes I'm going to start, okay, like normal, left-hand side, right? Secant squared theta minus tangent squared of theta. And I go, well, what can I do here? Secant, we've got 1 over cosine squared of theta. Your tangent would just be sine squared theta over cosine squared theta. All right, now that would be equal to, let's see, we have common denominators, so just subtract across the numerators. 1 minus sine squared theta over cosine squared of theta. Okay, so then I've got my Pythagorean theorem identity there. That's just cosine squared of theta over cosine squared of theta, which is just 1. Okay, so like right here, we're in the middle. I don't know how to get to the right-hand side unless I have some sort of crazy knowledge. So what we're going to do is we're going to go and work on the, kind of like in parallel, on the right-hand side. So let's manipulate the right-hand side, and maybe, just maybe, we'll end up with 1. So tangent theta, cotangent theta, that is equal to, what do we have? Okay, tangent is just our sine of theta over cosine of theta multiplied by our cotangent, which is cosine of theta over sine of theta. Well, cancel out everything pretty much because your sines and your cosines all drop out and you're equal to 1. So really, if you wanted a left-hand side, see how we just met in the middle? So we can actually continue this proof now because we know what has to happen with 1. You actually work back reverse. Okay, so on your left-hand side, you've got 1, which is in the middle. Okay, so after 1 comes the next step of sine theta over cosine of theta multiplied by cosine of theta over sine of theta. What did I do to that 1? I just multiplied the 1 by more 1s, right? So then that technically is now equal to tangent of theta cotangent of theta, which is our right-hand side. So we just forced our left-hand side to be equal to our right-hand side. Okay, through kind of the process of meet in the middle. I kind of like cheated, right? I kind of manipulated both sides so that I figured out what happens after 1, and you can complete your little proof. All right, so to recap, when you verify identities, you can start on the left and go to the right. I didn't really show you a start on the right-hand side to end up at the left, but I think you can handle that. Or you can do this meet in the middle sort of technique. All right, so that completes that. I hope you have a wonderful Memorial Day, and we'll be back